Okay, so good morning everyone and welcome to FK's Machine Learning Coffee Seminar. Today we have the presentation by Zheyang Shen from Aalto University, and he will be talking about de-randomizing Markov chain Monte Carlo dynamics with the diffusion Stein operator. And as always, so you are welcome to ask the questions already during the presentation, and I will then say them aloud when you write those to the chat, and after the presentation we have good time to then for the joint discussion. But please, Zheyang, the floor is yours.
Okay, so yeah, I can start now and I will share my screen. Okay, I hope everyone can see the screen now. And yes, I want to thank everyone for coming to the talk. And yeah, today my topic is about de-randomizing MCMC dynamics with the diffusion Stein operator. I'm Zheyang, and I am a doctoral student in the probabilistic machine learning group from Aalto. And my presentation is about the paper of the same title, which was accepted to NeurIPS. And my co-authors are my two supervisors, Markus Heinonen and Samuel Koski. And so, I think as the title probably suggests, the main focus of our discussion today will be about probabilistic modeling, or more specifically about our normalized distribution, which is a very common task when we talk about probabilistic machine learning. Since a lot of the tasks involve the inference of normalized densities. So we have the pi bar density available, but we don't really know, or we can't compute the normalization constant of the distribution. And of course, this is a very common setting in a series of different tasks in machine learning, such as the Bayesian inference or energy-based models or graphical models. And of course, when we talk about evaluation of unnormalized probabilistic models, they critically depend on the inference of such models, which I think speaks to the importance of Bayesian inference. And of course, there are conventional tactics in inferring unnormalized distributions, the most prominent of which involve either Markov chain Monte Carlo sampling or variational inference. Okay, so MCMC sampling basically simulates a Markov chain that eventually draws random samples from the target distribution, which we denote by pi in this context. And MCMC is asymptotically correct in the sense of that if we run the MCMC sampling for long enough time, we eventually, the MCMC chain eventually converge to the target distribution. However, the randomness in simulating the MCMC makes it very necessary that we run very long simulations so that we can obtain a large amount of samples. I think the randomness here is twofold in the sense of that there is intrinsic randomness in simulating the Markov chain, and there is the randomness of the samples drawn by the MCMC algorithm. And alternatively, we also have variational inference as a probabilistic inference tactic, in the sense of that we approximate the target distribution with a simpler parametric distribution from what I assume to be a family of parametric distributions. How we select such parametric distributions is usually an optimization problem. Yeah, of course, in the conventional variational inference setting, we optimize we optimize the distribution so that we minimize the KO divergence between the parametric distribution Q and the target distribution pi. And here is a very conceptual visualization of what the two methods are doing. So if we have this rather asymmetric target distribution pi, if we approximate the pi x using, like, for example, Gaussian distribution, then we might get like this symmetric approximation of pi, which is of course not entirely correct. And if we draw random samples, then we have this collection of purple dots from pi, which can also be a representation of the target distribution. And when we talk about de-randomize the MCMC sampling, we are, here I'm referring to the fact that we want to propose a deterministic sampling algorithm that emulates the behavior of MCMC, but instead transports interacting particles from what I assume is an initial distribution towards the target distribution. So in this context, if we have this target distribution pi, then we can initialize a set of n particles and deterministically optimize them towards a representation of the pi distribution. So what we have here is that we have an algorithm that has deterministic update rules, and that can utilize an MCMC type of parameterization. And we can also use, and it also has the feature of flexible particle representations with high quality samples. So, like, for example, these set of particles, they are not intrinsically random samples from the target distribution. However, if we view the set of particles as a set, as like in its entirety, then it constitutes a more accurate representation of the target distribution. And what we do in de-randomizing the MCMC dynamics, we start from de-randomizing the Langmuir diffusion, or Langmuir dynamics as a different word for the terminology. Langmuir dynamics is, of course, a very simple type of MCMC sampling algorithm where we basically simulate the stochastic differential equation, denoted by this equation here. In unnormalized distribution, we of course have access to the gradient of the log likelihood of the target distribution, since the gradient is not dependent on the normalization constant. And if we simulate this Langmuir dynamics, then we mostly get this discretized steps, which is in the form of a gradient descent, or I guess more accurately, a great ascent, which is also interfered by random noise, which is of course calculated. On the right side, this plot suggests a simulation of the Langmuir diffusion. So yeah, so basically we simulate discrete steps for a rather long time to infer the underlying target density, which is denoted by this contour plot in the background. So we basically run a gradient ascent with injected noise and run and basically after a set of burn-in steps, we extract random samples. The most common practice is to extract every fixed amount of steps, which is denoted by the black scatter plot in this visualization. Yeah. As it is like a common property for all MCMC sampling, Langmuir dynamics is also asymptotically correct, as in that the marginal distribution of xt when we simulate an SDE like this, when the time goes to infinity, it eventually becomes the target distribution. And it is the asymptotic exactness which we will discuss in more detail later in the presentation. So one way to see that Langmuir dynamics is asymptotically correct is to look at the Fokker-Planck equation. So while this stochastic differential equation, they have random paths, we can still characterize the marginal distribution of each time step using a partial differential equation. And here I write the partial differential equation in basically several shorthands, in the sense of if we denote the density at time t as rho t, then basically rho t is a function jointly by with respect to the data space and time. And we denote the partial derivative of this function with respect to time as the rho t dot. And the partial derivative of the marginal density corresponds to basically this notation, which corresponds to a divergence operator, or more specifically, the operator that sums up all the partial derivatives in this vector valued function. And it is the divergence operator of basically the marginal density times the gradient of the target distribution minus the gradient of the marginal density, which we can basically omit the x in this equation to write in this way. And if we assume the marginal density at each time t as known, which is obviously an unrealistic assumption in practice, we can show that this ordinary differential equation shares the same Fokker-Planck equation of as the Langmuir diffusion. So in other words, the marginal density of this ODE coincides with the marginal density of the Langmuir diffusion. So therefore, we can use the ODE instead of the SDE to simulate samples from the target distribution, which is called particle-based variational inference. So what we do in this context is that we first sample a number of particle samples from an original distribution, denoted by ρ0. And we update and then we update each particles using this ODE, where we estimate the basically gradient of the marginal density using those particles. And the next step of the particle-based variational inference is to basically internalize or eliminate the necessity of the gradient estimate by projecting the drift term in the ODE onto a reproducing kernel Hilbert space. Or more specifically, it is an operator valued RKHS. And yeah, if we do that, then we have this ODE, where the update steps corresponds to the expectation with respect to the current marginal density of this of this equation. If we approximate the marginal density using its empirical particle representation, then we basically replace this with a Monte Carlo sum of basically the right hand of this equation. So in the context of a particle-based variational inference, we therefore can construct what we call the Stein variational gradient descent, or the SVGD, by updating the particle using basically a weighted average of the gradients on each particle, and the weight is decided by a kernel function. And a repulsive force, where this nabla2 representation implies the partial derivative with respect to the second argument of the kernel function. So instead of simulating a stochastic differential equation, the SVGD runs this interacting particle system, where they update each particles with a summation of the weighted gradient estimated at each individual particle locations, and the repulsive force that basically prevents the particles from collapsing into the modes. And I think what is interesting here also is that this operator on the function kxt is also known as the Langmuir-Stein operator, or the Stein operator, in a lot of earlier works. And the Stein operator has the property of, if we apply the Stein operator on a certain set of functions, they will map a set of functions to a different set of function with the property of having expectation 0 with respect to the target distribution. And apart from using it in the context of particle-based variational inference, the Langmuir operator was first proposed to basically calculate what we call the kernel Stein discrepancy, which is a discrepancy measure between a set of samples and basically an unnormalized to a target distribution with unnormalized density. And we can see a comparison between the Langmuir dynamics and the Stein variational gradient descent. What the Langmuir dynamics is doing is that it simulates basically a single particles that basically temporally draw a set of samples from the target distribution, which is, of course, a random process. The Stein variational gradient descent instead keeps track of a selection of particle samples, which was initialized somewhere around here. And they are updated using the interactive rule so that the particle samples eventually spans out the target distribution. And all of those, or what we call the de-randomization of Langmuir dynamics, was from the previous works. And what we are proposing in this paper is to use this framework to a much larger family of MCMC algorithms. And what we are doing is also similarly basically deconstructed into 3 steps. First of all, we find a diffusion-based MCMC sampling. And then we take a look at its Fokker-Planck equation and construct an ordinary differential equation that shares the same evolution of distributions. And lastly, to internalize the gradient estimate, we project the drift term in the ODE to a reproducing kernel Hilbert space. So we basically extend the connection between Langmuir diffusion and the SVGD into a larger set of MCMC algorithms. So what we call the MCMC dynamics can be more accurately described as diffusion-based MCMC sampling. What this means is that we consider Markov chain Monte Carlo algorithms that are diffusion processes that evolve towards the target distribution. So we consider the MCMC algorithm that can be written as this type of stochastic differential equation. So in this equation, it takes the MCMC dynamics takes 2 parameters. So the first parameter A is a positive semi-definite matrix-valued function. And the second parameter C is a skew-symmetric function. So in this SDE, we have the drift term and the diffusion term. So we update the basically MCMC particle using the gradient of the target distribution warped by the A and C matrix. And we correct the bias by also introducing basically the divergence of the A and C matrix, which is actually defined by the divergence of each column vector of the A and C matrix combined. And then we inject noise according to the positive semi-definite matrix A. And this framework is proposed by this rather well-known paper, and they managed to show in the paper that this SDE represents the entirety of Ito diffusion processes that can be used as a sampling algorithm. And of course, there are a myriad of different examples of MCMC dynamics. The first and most simple example is the Langmuir diffusion, where we have basically an identity matrix A and a zero matrix C. And we already know what a sample path of the Langmuir dynamics look like. And we can also construct Hamiltonian Monte Carlo in this way, where we have a zero matrix A and this skew symmetric matrix C. And I added a star in this with respect to Hamiltonian Monte Carlo is that, although the parameterization of the HMC corresponds to the MCMC dynamics, the HMC itself does not produce random samples from the target distribution, because if we take a look at the HMC formulation of this SDE, then we know that it basically runs around in circles, and HMC only becomes a valid sampling algorithm when this dynamic is combined with a jump process that periodically resamples the momentum variable. So a bit counterintuitively, HMC is not included in the scope of discussion of MCMC dynamics. And of course, we also have the stochastic gradient Hamiltonian Monte Carlo, or in a lot of other statistics contexts, it's called the underdamped Langmuir dynamics. And I used basically the specific parameterization of what I simulated in this sample path, which is that we have a diagonal matrix A, except that it is zero in the first dimension. And then we have this skew symmetric matrix C. So what this does is that the C matrix basically circles along the contours of the target distribution, and the A matrix is like a friction term that gradually evolves the particle towards the basically maximum likelihood solution. So of course, then the sample path of the SGHMC is very much different from the Langmuir dynamics. So it is basically, it basically has this circular motion that gradually evolved towards the center. And if we draw a random sample every a couple hundred steps, then we get a collection of samples that are represented in the black points here. And just the same as the previous investigation of the Langmuir dynamics, we know that we should also take a look at the Fokker-Planck equation of such SDEs. And what this gives, of course, this is not a standard form of the Fokker-Planck equation, but we show that this partial differential equation is equivalent to the standard form of Fokker-Planck equation. So this of course includes the Langmuir diffusion as a special case where we have A equals identity matrix and C equals 0. And if we apply the same logic with respect to de-randomizing the Fokker-Planck or de-randomizing MCMC dynamics into an ODE system, then what we have is that is an ODE where the particle updates are basically the difference between the log likelihood of the pi distribution and the log likelihood of the marginal density at time t, warped by the A and C matrix. Which, of course, here we also need to estimate the marginal density at each time step t. And what we do in de-randomize the MCMC dynamics is also the same as to project the vector that is the ODE update of the de-randomized MCMC dynamics onto a reproducing kernel Hilbert space. And similar as before, that this projection basically turns the gradient of the log likelihood of the marginal density at time t into an estimation, into an expectation, sorry. And this results in an ODE, which we have an estimation with respect to the current marginal distribution. And we again have like a weighted average of the drift term in the original MCMC SDE function. And then we also have a repulsive force, which is basically the same as taking the gradient with respect to the second argument of the kernel function. And we also warp the gradient with the A and C matrix. And if we combine these two, we obtain the diffusion Stein operator. So like, again, if we keep track of a particle, of a set of particles, we can estimate both terms with Monte Carlo system. And then we have an interacting particle systems that also emulates the behavior of Markov of this particular MCMC dynamics parameterized by the specific A and C matrix. And again, the diffusion Stein operator is a generalization of the original Langmuir Stein operator. And it similarly has the property of mapping a set of functions to functions of expectation 0 with respect to the target distribution pi. So we can see that there is this interesting equilibrium in this kind of particle update system, where, for example, if we update the particles using this ODE until they stop moving, then we know that the particle update, while being estimated at basically discrete points, they share the same expectation with respect to the target distribution. And and basically this paper below originally proposed the diffusion Stein operator also in the context of estimating a discrepancy between a set of samples and a set of samples and an unnormalized density. If we take a look at the generalized SVGD, we can, I have this visualization here, which we have the original stochastic gradient HMC sample path, which has this circular while drifting to the center motion. And if we use the exact same parameterization of the A and C matrix and update a set of deterministic particles, then what we have is that all the particles still jointly shares this basically circular motion towards the center, except that we control that by particle interaction. And they also eventually converge to a span of the target distribution. So, like visually, we can see a similarity between like a sample path of an SDE and a collection of traces of an interacting particle system. And yeah, the basically duality between the SVGD and the generalized SVGD goes beyond the, what we have just derived. We can also see the G SVGD as a steepest descent within a reproducing kernel Hilbert space that minimizes the KO divergence. What it does is that the particle update, which is the diffusion Stein operator estimated on the expectation of the current distribution, is the one in the RKHS that maximally decreases the KO divergence if we think about an infinitesimal transformation from the current distribution to like an infinitesimal change to the current distribution. And of course, there is also the line of research that talks about that talks about the evolution of distribution as a vector flow in the Wasserstein space of probability measures. And what this changes is that the generalized SVGD can also be explained in this way. And of course, there are many different benefits that we obtain by introducing this parameterization of A and C matrix into the system. So we can basically combine a deterministic quasi-MC Monte Carlo algorithm with many standard practices in the MCMC. For example, we can introduce additional momentum variables that we use to accelerate the inference, in the style of the underdamped Langmuir dynamics or the stochastic gradient HMC. Or we can introduce a more flexible Riemannian parameterization of the A and C matrix that also speeds up the inference. Of course, like besides the 2 points that I just mentioned, there are also a selection of the standard practice in MCMC that we can adapt into a deterministic system. For example, we can have a leapfrog update when we have momentum variables where we update momentum variables using half steps. And we can have the momentum resampling similar to a Hamiltonian Monte Carlo system where we routinely resample the momentum to obtain new samples. And here is basically a toy example of what we do, of the advantages when we introduce a more flexible parameterization of the A and C matrix. here we actually have basically the same target distribution as the previous illustrations, except that we have we have a multimodal target distribution. And of course, we can run like Stein variational gradient descent, or we can basically run a de-randomized version of the Riemannian Langmuir dynamics, which here I denote as the Riemannian SVGD. Or we can run or we can run an SGHMC with Stein parameterizations. And finally, we have like a stochastic gradient, Riemannian Hamiltonian Monte Carlo, that we use to parameterize the interacting particle systems. And we can see that like for the particle-based variational inference, it's often not easy to determine multimodal distributions. But with the help of more flexible particle representation, we can have this type of very different particle paths that first spans out and then like gradually locate to span the individual modes of the target distribution. So yeah, in conclusion, what we discovered in the paper is that the duality between the Langmuir dynamics and the Stein variational gradient descent also extends to like a large class of diffusion-based MCMC dynamics. And yeah, on the other hand, therefore we can transform MCMC dynamics to interacting particle systems with the similar behaviors. However, I think that there is like still a lot of open questions with respect to with respect to the behavior of interacting particle systems. So for example, there are multiple ODEs that correspond to the same Fokker-Planck equation as the MCMC dynamics. And we have yet to discuss like which parameterization of all the equivalent ODEs, or do they have like, are they the same, or do they have like different optimality? And for a deterministic system, it is technically a biased MCMC sampling algorithm. And how can we address such bias? And yeah, finally, and I think that is the most important questions, especially with respect to practical application of such methods, is that how do we choose the kernels? And of course, we used a very trivial operator valued kernel. And of course, there are multiple different ways to augment that framework. And I've also included the archive link of the paper. And that is the that is the entirety of my talk. Thank you for listening.
Well, thank you for a very interesting and clear presentation. So we would have time for one question. So who would like to take the honor? You can raise your hand or open the mic if you wish to ask something. Okay, if no one else also, then I will take the opportunity. So in the beginning, you were saying that with the traditional MCMC method, so you experience long simulation times and you need large amount of samples. So could you comment something now about your method? So how would this improve the situation with respect to those issues?
Oh, okay. So I also mentioned that the MCMC sampling algorithm is basically like the randomness comes from two aspects. One is the randomness of the samples drawn by the simulation of the Markov chain. The other one is the randomness within the simulation. And of course, we assume that like simulating a random or a stochastic Markov chain is, it converges slower when compared to like a more optimization style paradigm. So what I think is that like a deterministic particle-based system, it basically has a faster convergence for the fact that it is deterministic. Also, the set of particles that we choose has more high quality samples when compared to, like, for example, the random samples that we randomly draw from the distribution, so that it's collectively the particle samples give a more accurate representation of the distribution.
Okay, great, thank you. So if one quick question still arises, we still would have time for that. But no, so I guess we are then fine. So thank you very much for the presentation, and thank you everyone for listening, and I will then see you again next week.
Yeah,
Bye-bye.
thank you very much.
Thank you.
Yeah.
Bye.